Hi, I am Dr. Sayan Das, radiation oncologist from Kolkata. Uh, a very good evening to you all, and I wish you a very happy New Year 2021. Today is day 4 of our course on critical appraisal of medical literature. We have had few fantastic sessions in the last few weeks, and we hope that is going to continue today as well. Today we have two important sessions. One would be on how to interpret the results of correlation and regression analysis, and the other one would be delving deeper into systemic reviews and meta-analysis. For the first session, we have with us Professor Nilotpal Chowdhury. Those who have had participated in our course 1 on fundamentals of biostatistics, they all know who Professor Chowdhury is. So there he did discuss some points about correlation, which he would finish today and then move on to the interpretation of regression analysis as well. Professor Chowdhury is currently a professor in the Department of Pathology and Laboratory Medicine at All India Institute of Medical Sciences at Rishikesh. Professor Chowdhury, please.
Thank you very much for inviting me over here. Uh, Today, I'll be taking a lecture on regression. I'll be sharing my screen now. Okay. Uh, is the screen visible?
Yes, sir.
Okay. Thank you. Thank you for today's lecture on regression. What I'll be doing, this is the plan of my class. I'll be first revising the concepts on correlation, which I had taken last time. That will serve as a refresher. Then we will get into the basic concepts of regression. We'll just discuss that regression is basically fitting a line with error. We'll discuss how to interpret the results of a regression analysis, how to check the assumptions, and how to compare different regression models. In this session, I'll be dealing mainly with linear regression. But now let's start over here. Let's start with correlation. Now, correlation basically, when we speak of correlation in statistics, correlation coefficients finds the linear relationship between two paired variables. There may be a nonlinear relationship, mind you, which is not picked up by a correlation coefficient. That's why we have to graph the data. Now, any correlation coefficient, the values range between -1 to +1 with 0 in between. A value of the other variable decreasing. There may be 0. 0 means there is no correlation. And correlation coefficient of 1 means that also increasing. Now, once you have Gaussian variables, that is variables following a Gaussian distribution, Pearson correlation is the method choice. What if the variables do not follow a Gaussian distribution? You can do either a Kendall correlation or a Spearman correlation. You can find a Kendall correlation coefficient or a Spearman correlation coefficient. For these two interval. And one
Dr.
thing you have
Chowdhury,
to.
if I may interrupt you, could you kindly switch off your video?
Yes.
Because of
Okay.
because there's poor connectivity. So the audio gets interrupted at times. Yeah, thank you.
Okay. Uh, we have to understand that high correlation does not imply agreement, but a high correlation coefficient does imply low random error. Now, what we do in a correlation coefficient, we graph it. We graph it, we use something known as a scatter plot, and the shape the very strong and a high correlation coefficient. We have the values centered around the line joining the either the bottom left to the upper right corner, or from the top left to the bottom right corner. When the values actually seem to be the points seem to go from the bottom left to the top right corner, that means that it's a positive correlation. When the values seem to go down, that is from the um, top left to the bottom right corner, that implies that the correlation is negative. And as the correlation coefficient decreases and goes towards zero, the points spread out to fill the space of the scatter plot. I made this point earlier that near zero correlation coefficient does not. For example, there's a yeah, this is this scatter plot shows y related to x in such a way that y is equal to x square. It, it gives a correlation coefficient of very near zero, but there is a definite relationship. So a near zero correlation coefficient does not mean that relationship between variables do not exist. We should be plotting the data. So with this background, we move on to regression. Okay, so these are the points we'll be covering. We will discuss the concept of mainly linear regression, that is fitting a line with error, the interpretation, assumptions, and how to compare models. Now, regression. Regression is just a method of predicting one dependent variable from one or more predictors or independent variables. So we have two new terms over here right now. Now, if the variables are linearly related, we use or try to use basic schoolboy or schoolgirl algebra. That is y is equal to mx plus c. Some textbooks give it as y is equal to a plus bx. That's the equation for a straight line. We try to see if y and x are related. We have built straight line equations with errors. And over here, once we solve for y is equal to a plus bx, the x variables are the predictors. And what we are predicting, the predicted variable, that is the y, that is the dependent variable. So, what the variable we are trying to predict, that is the dependent variable, and the predictors are the independent variable. Many times, the regression does not follow a linear form. In that case, we may try to transform the data, but that is something else. Now, once we know the dependent variable, what type of regression to use depends on the nature of the dependent variable, not of the independent variable. If the dependent variable is continuous, we may try a linear regression. Linear regression is a common solution to such a problem. However, if y is a dichotomous variable, then we try to predict the the natural log of the odds, and we use a logistic regression. If the dependent variable is a time to event variable from which we can calculate the natural log of the predictors can be anything. The predictors can be continuous, categorical, ordered categorical. We can use any type of predictor in linear regression. Linear regression is linear. While going for linear regression, we have to know a few concepts about what is the intercept, what is the slope, what are the residuals. I have focused on I have a graph on the right hand side of the screen over here, and there are points. You will see that there are some certain points, and I've tried to fit a line of best fit through it. Once we have fit the line, the difference between the y values and the fitted line, these straight lines, these are known as the residuals. And the intercept is the value of the line of best fit when x is 0. The intercept is the line of the best fit when x is 0. Now, just vary along a straight line which is parallel to the y-axis. They are supposed to indicate measurements y variable. That is one of the primary limitations of the linear regression. That's a primary assumption and limiting factor in any linear regression. That is, in linear regression, all errors, the predictors are assumed to be measured. Once we now let's get into the slope. For the slope, we can have no slope. Slope is equal to 0. A slope of 0 means that there is no relationship between the dependent variable and the predictor. A positive slope, a slope greater than 0, where a straight line goes from the bottom left to the top right corner. A positive slope shows positive association between the dependent variable and predictor, and a negative slope shows a negative association between dependent variable and predictor. What is important over here is we have to realize that the slope can take any value from minus infinity to plus infinity. It is not between like for correlation coefficients between -1 and +1, checking out whether there is some association or not, whether the slope equals to 0. We test against a null hypothesis negative. Now, I'll be going into the interpretation first, and then I'll get into the assumptions, because usually in statistical programs, you get the results first, and then you get various assumption plots. Now, how to interpret the results? Once you do a regression analysis, you will be getting some results like this. You'll get coefficients, a term known as intercept, with a value for the intercept estimate with a standard error t value probability. And again, for x, for any x variable, an estimate, standard error, and probability. Once you get something like this, you see over here X estimate is 0.93322. The intercept value is 2.98405. This just means that the equation is for the y variable, y is equal to the value of the estimate for x, in this case 0.93322x, plus the value for the intercept 2.98405 plus error. So this is the equation y is equal to mx plus c or a plus bx. Over here, the m or b represents the slope. This is the slope 0.9322x, and the intercept is plus c or plus a depending on which book you study. The intercept 2.98405 plus error, and the fit depends on how big the error is. Besides this, in the results for any linear regression, you're also going to get certain other values. For example, the residual standard error, the multiple R squared, adjusted R squared, F statistic, and a overall p value. What do these mean? What is most important is over here, besides the equation, to check out for the multiple R squared and adjusted R square. The multiple R square and adjusted R square show how good the fit of the model is, how good the predictors are actually predicting the dependent variable. These range from 0 to 1, and values close to 1 show a very good fit. In this case, for this example, the value of the adjusted R square is 0.9278. That's quite close to 1. We can say quite reasonably that the model that we have put over here, that is y is equal to 0.9322x plus 2.98405, that's a good fitting model. The overall significance is given by the F statistic, and for the F statistic, p-value is given, and this p-value shows that whether the model is statistically significant or not. And besides this, we also have to see whether the x coefficient is significantly different from 0. This can be seen by checking out the standard error, okay, or by checking out the p-value, ideally both. Now, with the multiple R square and the adjusted R square, I will advise you to use the adjusted R square more. Why? I'll come into later. And we should also check out how significantly the intercept differs from 0. In quite a few analyses, the value of the intercept is important. For example, in accuracy analysis. So we should also check how significantly the intercept differs from 0. Now, what do these mean? The residual standard error, the multiple R squared, the adjusted R square. Let's see. A low residual standard error implies better fit again, but there is no also another statistic known as the root mean standard error, RMSE, which is just the square root of the residual standard error divided by as a result of which we cannot. That's why for beginners, I always say that you should depend on the multiple R square or better, the adjusted R square. The multiple R square is often used as a goodness of fit measure. The problem with multiple R square, and that is why I always advise to use, or statistical textbooks also advise to use the adjusted R squared, is because the In case of multiple regression, the multiple R square increases as the number of explanatory predictors increase, and a high value may just imply a good fit due to a high number of predictors. That high number of predictors is adjusted by the adjusted R square value, and that is why uh, the adjusted R squared value is a better statistic to be used to assess the degree of fit. Now, so once we know what the various statistics means, what are the various assumptions made while doing a linear regression analysis? First assumption, and it's a very important assumption, is each and every subject should be independent. Number two, there should be a linear relationship between predictor and dependent. For example, if y is equal to x squared, that's not a linear relationship. You can't fit. In that case, you may have to transform the y values, the dependent values. The residuals, that is the difference between the line of best fit and the dependent values, that should follow a Gaussian distribution. The residuals should have a constant variance across all the fitted values of the predicted variable or the dependent variable. And the independent or predictor variables are assumed to be measured, assumed to be there for the dependent variable. So, how do we check the assumptions? For the linear relationship, to check out whether there's a linear relationship between predictor and the dependent variables, we do it by means of a scatter plot. Plotting the data by means of a scatter plot is one of the most important things to be done at the beginning of the analysis and during the analysis. Now, the residual should follow a Gaussian distribution, and the residual should have a mean of 0. This is done by two different plots. One, a quantile plot of the residuals. It's also known as a normal plot of residuals, as well as a plot of residuals against the fitted y. We will show the examples just after this. The residual should have a constant variance across all values of fitted y. This is again done by a plot of residuals against the fitted y. And we should always realize one thing. Regression models are sensitive to outliers. It's really agreed, or one of the general recommendations is that subjects having a Cook's distance greater than 1 or markedly greater than others should be examined. If necessary, they may be deleted. Now, how to check the assumptions? The assumption of linearity is assessed by a scatter plot. As we see over here in this example, the points seem to be around a single line. So over here for this analysis, the assumption of linearity is met. Then the Gaussian distribution of residuals are assessed by means of a QQ, quantile plot, a special case of a quantile plot known as the normal plot. Over there, the residuals should follow an approximately straight line. It should be approximately on a straight line. For this particular assumption for which this testing has been done, these lines seem to follow the straight line. There seems to be a slight deviation. That's not a very big deviation in my opinion. According to Bland and Altman, what they do is they say, take the plot put a thick pencil over the lines. If all the points of the QQ plot are covered by the thick pencil, the assumption of a Gaussian distribution of the variable or a Gaussian distribution of the residuals can be accepted. And third is this is by the residual plot against the fitted Y. Over here, we have to see whether these are the residuals and the x-axis has got the fitted Y. We have to see whether the residuals are uniformly spread across the plot with equal width and a mean of 0 centered around 0 for this plot. In this case, that seems to be the case. Over here, the statistical program has also tried to draw a so-called smooth line over the fitted values of Y. That line does not seem to markedly deviate from 0. That smooth line should form a squiggly line around 0. That seems to be the case over here. So even in this case, the assumption seems to be met. How do we check for the influential observations? Influential observations are assessed by a plot known by as the residuals versus leverage plots. And usually in the residuals versus leverage plot, there is a line representing the Cook's distance, zero point 0.5 or point or 1 over here. In this case, there is no line. So I'll just show a plot from a different analysis which shows the influential distribution and how the Cook's distance looks like. You can see over here dotted curved lines representing the Cook's distance. And if there is any point going above 1, they should be examined carefully. Or if, if one of the values are markedly different from the others. So in this case, for the left-handed graph, the residuals versus leverage plot seems to be adequate. Uh, and we can go on for the analysis. So keeping this in mind, let us see what are the differences between the correlation and linear regression. Now, in correlation coefficients, the x and y variables are assumed to have the same magnitude of errors. In linear regression, the x variable is supposed to be measured without any error. All errors are there in the y variable. In correlation coefficients, no variable can be controlled or manipulated. For linear regression, you can have different values of x. By experimental design, you can put in different subjects having different predictor values to see how that affects the y variable. And the predicted or the dependent variable. Two variables are estimated. In linear regression, you can check out the association between one dependent variable and multiple predictors simultaneously. And multiple predictors having continuous or categorical or ordered categorical. So for checking out simple association, and linear regression holds multiple advantages over a simple correlation analysis. Let us look at an example. Now, we have a study in which the experimenters try to find out the height of an individual of various individuals, uh, and they try to predict the height from the hand length and the foot length. So over here we just have a short snippet of the data over here. There's the gender, the height of the individual in millimeters, the hand length, and the foot length. Now, let us, for an example, we will be replicating the analysis initially only for males, and then we will see whether the equation for males and females, whether they can be combined together. and how good the fit is. So we will start by asking a simple question. Can we predict height of males from their hand length? So once we put in the data, we get uh, some values like this: coefficients, hand length, we have got an estimate, standard error, p-value, intercept, the value of the intercept with its standard error, the residual standard error, multiple r squared, adjusted r square. What this means is, for the hand length, we have the estimate of 4.8049 and the intercept 747.4174. This just means that what we are saying is height is equal to 4.8049 into hand length plus 747.4174 plus error. What we have to keep in mind are the units. Over here, both the height and hand length are in units. So the height in millimeters is equal to 4.8 into hand length in millimeters plus 747 plus error. Had the units changed, the intercept, the value of the intercept also would have changed. Now, let us look. Is it a good fitting model? The multiple r square is 0.5212, a moderately fitting model, let's say. It's uh, somewhere in between 0 and 1. It's not very poorly fitting, not very good fitting either. And however, there is a significant association between hand length and height as given by the p-value both of the overall model as well as for hand length alone. Now, while we do this, we should always check out the assumptions. We check out the residuals versus fitted. The residuals seem to be a closely around zero, but there are one or two outliers. We should examine whether these outliers are actually influential or not by the residual plots. The QQ plot, there is marked deviation from normality. So there is, so that may explain some of the poor fit, and maybe we need to examine the data better, possibly exclude some outliers. And for the residuals versus leverage, there seems to be no observation which is markedly greater than having a Cook's distance greater than 1. So we have this, the assumptions are not perfectly met, but what to do? We may do the analysis, we may try to do the analysis after removing the outliers, or may try another thing. We may try to improve the model by, say, adding foot length. So, can the model be improved by adding another variable? What to do in this case? What is the procedure used? What we use in this case is something known as a multiple linear regression. Now, for multiple linear regression, algebraically, it takes the form of y is equal to m1 x1 plus m2 x2 plus going into c, where the m1, m2 to mn are also called the partial regression coefficients, and x1, x2 are the multiple predictors. What should be known for multiple linear regression is that the predictor should be independent and to have stable estimates of the coefficients. They should not show any association with the other. This assumption, also called the assumption of non-multicollinearity, should be met. In practice, it's often not met, as we shall see in this example itself. That is a Gaussian distribution of residuals centered around zero, an equal variance of residuals across the fitted line, and no influential observations. And the interpretation of the partial regression coefficients is same as the interpretation of the slope, the interpretation of the intercept, and the at the adjusted R square are similar to that of simple linear regression. And we should be very, very cautious against too many predictors. Too many predictors may lead to unduly optimistic values and may lead to overfitting. Now, coming back to our example, we had this equation over here, height to hand length. Height is equal to approximately 4.8 into hand length plus 747.4. We do the model be improved by adding foot length. We do the analysis and we get the results over here. Once we get this, the first thing we look at is the multiple R square. The multiple R square over here is 0.7. Multiple R square for having the model in which just there was the hand length was 0.52. So there is, let's say, a marked improvement in the model. Okay. Now, I've already told you that multiple R square is not such a good statistic. If we use the adjusted R square, it is around 0.69 over here. Still, 0.69 in this model having foot length plus hand length to uh, around zero point 0.5 previously in the model having just hand length. It is a marked improvement over here. So once we see that there's some improvement, we get into the coefficients. We look at the estimates of the foot length plus hand length, and we have a different equation over here. Over here, we get a new regression equation. Height is equal to around 3.2868 into hand length plus 2.3808 into foot length plus 439. So we get a totally different uh, regression equation over here. And this regression equation is shows a better fit uh, compared to the previous one. However, we should always go and check out the assumptions. We check out the residuals versus fitted. What we see as compared to the previous data, the residuals are closely clustered around zero. Number of outliers seems to have gone down. There were more outliers earlier, but there are still outliers. The normal QQ plots, there are still two plots which show a marked deviation from normality, but on the whole, the QQ plot also shows a marked improvement. And influential observations. Additional assumption for multiple regression, the assumption of multicollinearity and linearity. First, check out the linearity of the added variable. We see that to check out the multicollinearity and the linearity, we do the scatter plot of foot length and height, and we find out that height and foot length are actually closely related. There's a Pearson correlation of 0.47 between height and foot length. This shows a moderately strong linear relationship. And the importance of this is for the final model fit, it may not be that interferes with the suppose if we had gone into this analysis trying to show whether foot length and hand length show independent information over the other, in case of multicollinearity, we may have had spurious results. The improvement in the model can be checked by the, as I told you, by the adjusted R square, model having both improved when we added foot length to the model. So that's one part. So it has gone down. We can nation.
I think we have lost Professor Chaudhary because of poor connectivity. I would request the participants to kindly wait before he joins back. Meanwhile, Dr. Shantanu, are you there?
Yes, Dr. Stein, I'm there.
So, would you like to take up the question?
What I'm just was I'm sorry I didn't see the chat. What is the question? How do we safely omit the outliers to improve the fit? Are there any rules to do it, or should we exclude from all the analysis? Okay, so this is a very complex question because yes, there are rules, but they are more like general rules of thumb or general guidelines. In general, it depends on what exactly you are trying to study. So it will be a very much on a case to case dependent. I cannot give you general rules. uh, for the example which Dr. Nilotpal showed, for example, if it is outliers regarding the hand versus the foot length versus height, the relationship between them, we would like to see whether we would like to see whether some of these can be explained just by the selection of which we have. So if you have not selected, because it starts from selection of your data, if you have not selected your data randomly, or if your data itself, that is the raw data itself, is not uniformly distributed, then you will get this kind of things. What do I mean by that? Let me give an example. If suppose you're taking hand length and foot length and you're trying to correlate with the trying to get a relationship with the height, and you take a class of, let's say, 12th standard students, but let's say some of them are basketball pros or they are amateur basketball players, you would expect them to have longer hands or fingers and or height. Let's assume you have two people who have Marfan syndrome. You would expect them to have longer finger spans, won't it? So that kind of data, I think you'll have to get into your data set and see what exactly explains the outliers. And if you believe that these outliers are not representative of your real data, in that case you may uh, omit them, but you'll have to state very clearly why you have omitted those data points from your data set. Does that make sense? I hope that makes sense. Am I audible? I don't know
Yes,
whether.
yes, yes, you are.
Okay, so I hope that made sense.
Yes, completely.
Okay, one point I would like to make since Nilotpal, till the time Nilotpal comes back, is about non-multicollinearity. Now, even though, and this is very important, as Nilotpal already pointed out, this is very important when you are taking multiple variables. Once you go from single simple linear regression to multiple linear regression, you should be very careful in that the other variables are not related to each other. And sometimes you encounter something called as a sort of a Simpsons effect kind of phenomenon, that there are hidden variables which affect both of them. So, for example, in this particular example, the genes which code for hand length, some of them also code for foot length, and some of them also code for general total height in general. So even though statistically multicollinearity may or may not be there, that we'll have to see. However, biologically also you'll have to see whether these are actually independent or not. Because statistical methodology dictates that these variables should be independent of each other. If they are not truly independent, statistics cannot make out half the times. That is your job as a clinician or whatever you're trying to read. So for example, if I give a more clinical example, so let's see that you're trying to have an endpoint of MI, whether MI is there or not there. And you have multiple predictive variables out of which BP is there, and you have serum blood glucose levels, diastolic BP, blood sugar levels, and 5 other variables. And if suppose blood sugar levels and diastolic BP may or may not be linked to each other, that's fine. If you believe that they are independent, you can put them in a multiple regression model because they're supposed to be independent. But suppose you were to take something like left ventricular ejection fraction. Now that may be linked to diastolic BPs. Or if you were to take, let's say, you want to see the effect of serum aldosterone values or renin values on MI. Now it's quite possible that the serum renin or aldosterone values might be related and reasonably strongly related with the serum diastolic blood pressure values. So you should be a pretty good expert in your branch, and you should know search and you should have knowledge of the literature surrounding that whatever you're doing, to be able to make sense of A, how to actually build a good model, and B, if you have built it, how to really interpret it. Again, I hope that was useful.
Yes, very much. Uh, Dr. Chaudhary, are you there?
Yeah, I can see Nilotpal now. I mean, at
Yes.
least he's muted. Dr. Sayan, when I'm trying to message Nilotpal privately, it says Nilu is not in this meeting. I think he needs to add it or something, probably.
But he's already there. He's a co-host.
Yeah, maybe he's not joined himself. I don't know how he's doing this, but when I'm trying to message him privately, it says that he's not in the meeting.
Audible
I
now?
don't know what that means. Yeah, now it is.
Yes, yes, sir,
I'm,
you are.
I'm going to mute myself now.
Thank God. I'm very sorry. I'm very sorry over here for this. Uh, my internet connection seems to have gone off. I've gone for the alternate connection right now. Shall I continue the? I do not know how
Yes,
much.
sir, please.
Where was I? Over there when.
Will you please start sharing your screen, sir?
Okay. Uh, I do not know how much I missed. Where was I? Uh,
Yes, you were
when I
talking
got
about on this slide.
cut off, the internet got cut off.
Yeah, you were
Okay,
discussing this one.
we were discussing this one, and when we compared the two models, we can compare the models by looking at the adjusted R square values. So besides this, we had used this model for males. What about for females? For females, we will have different coefficients and we can have a different equation. For example, over here, we get an equation of height is equal to 2.37 into hand length plus 1.7 into foot length plus the intercept. For males, we had a totally different uh, coefficients. We can see that the coefficients for hand length are different. It is 3.3 for males, 2.4 for females. For foot length also, the coefficients were very different. So the coefficients are totally different for males and females. The equation is totally different. It would be unwise to combine both the genders into one equation. So in such a case, for all the categories, if that is not true, we should not be doing a linear regression, a multiple linear regression in this case. It would be wiser to use two different regression equations. So we can check the residuals, we can check the assumptions. Over here, we have checked the residuals versus fitted. We see an outlier over here. We can check out the QQ plot, and we can check out the Cook's distance. Now, once we look at the Cook's distance and the outliers, we see that there are certain moderately influential that had examining that. There was, of course, a relationship between the hand length and foot length, as a result of which there seems to be certain amount of multicollinearity, but there is nothing much we can do about it over here right now. But we should be looking at the influential observation. If we had left out the potential outlier, we would be getting a multiple R square value of 0.7. In the previous equation, when we did when we did include when we did include the outlier, the R square value was around 0.61. So just leaving out the potential outlier markedly increased the fit of our model. So identification of outliers and influential observations may lead to a better fit, and so they may be left out of the final fit. To sum up, for any linear regression, we first have to positive association. A negative slope means negative association between predictors and the dependent variables. We use adjusted R square as a measure of fit and to compare models. We should always check the assumptions. That is, residual should be spread evenly around 0 and should follow a normal distribution. We should always check for multiplication. In multiple regression, additionally, we should check if the regression equation is similar across all categories if there is a categorical predictor. These are the points I want to get through in this session. Thank you. Any questions?
Thank you, sir. Uh, I, there was a question, but that has already been dealt with while there was those network issues. Dr. Sapru chipped in with his observations. If there are any other questions, you can write it in the chat box, or you can unmute yourself and ask Professor Chowdhury directly. Okay, so there's one question is that how many variables are allowed in multiple regression models? Professor Chaudhary? I think there's again those network issues with him. Dr. Sapru, would you like to take this up?
Yeah, I don't mind if everybody's okay with it.
Yeah, please go ahead.
Okay, so there is no real answer to this question. You can have as many variables as you want as long as your regression model doesn't fail or is robust enough. That being said, generally speaking, one should have the least number of variables which are predictive enough for to develop a predictive model. So I really cannot. I don't think anybody can answer this question that how many variables are allowed. The more number of variables you have, the more difficult your prediction may be, even though your predict variables might fit better, but the predictive value of each variable may actually be decreased. So I honestly don't know. Dr. Tejpal Gupta is here. He is probably more of an expert than I am. Maybe he can answer this question in a more robust manner.
Tejpal sir, we would like to have your comment.
So I really don't know the answer. I think what Shantanu says just makes some common sense that so you should be having the least number of variables for the model to be most robust. Having said that, I think which variables to include in a regression analysis, I think that's more of a clinical call rather than a statistician's call. So therein lies the sort of need for a clinical input, not just pure statistical input that, okay, there are 10 variables and all should be included. So I don't know the correct answer, but I think the least number of variables that seem to be clinically important and meaningful should be included in a regression.
Thank you, sir.
Thank you, sir. So we'll now move on to our next session. So, so the second topic of the day today on day 4 would be systematic review and meta-analysis. That has already been covered to a large extent by Dr. Sapru in our module 1. Uh, Today we have with us Professor Tejpal Gupta. He's professor in the Department of Radiation Oncology in Tata Memorial Hospital in Mumbai. He looks after the neuro-oncology disease management group as well as the head and neck group, I believe, as well, sir. So, sir will be kind of delving deeper into the meta-analysis, and I think also be discussing his experience about what Cochrane is now planning to do with India, I think. So, sir, could you please start?
Let me just start sharing the screen. So is it visible now?
Yes, sir.
So good evening to everyone. I think as Sayan said, previously Shantanu has covered this, so might be somewhat of a repetition, but nonetheless, I'll try to sort of delve into what is a systematic review and meta-analysis and how to go about conducting one and interpreting and as well as reporting of results. I haven't actually included the Cochrane India Network logo here because that's still work in progress. The Cochrane collaboration has actually invited expression of interest from different stakeholders throughout India, and Tata Memorial Center is one of such entities, and we have submitted the application and have received the go-ahead for the final call. That's still awaited. So Cochrane India Network would replace, it would be a network of institutions within the country, which would represent the entire country, and South Asian Cochrane Network and Center, which was actually originally situated in CMC Vellore, will no longer be in existence. In fact, I mean, it's already not in existence. It is now the B.V. Moses Center of Statistics, Biostatistics. But the Cochrane India Network probably in 2021 will become live and functional. So to begin with, most of you are aware about the evidence pyramid, and systematic reviews and meta-analysis, and particularly the Cochrane reviews actually are highest on that pyramid and are the most robust evidence in for informing healthcare decision making. Just to briefly define what is meant by evidence-based medicine, and this is for some of the students and trainees. So David Sackett in 2001 actually suggested that, gave this definition that the conscientious, explicit and judicious use of the current best evidence in making decisions about the care of an individual patient. So it is the integration of best research evidence with clinical expertise and patient values. However, there are several reliable barriers to reliable evidence, and again, this is one of my favorite slides. I think for a live audience, it is easy to ask how many can answer this question: who loves whom? I don't know on the Zoom platform whether that can be possible, but it's difficult to make out here who's in love with whom and who's cheating whom. So there are several biases and confounders to reliable evidence. And the second barrier to reliable evidence is actually chance or coincidence. These are two photographs of Donald Trump. One of them is actually Donald Trump. The other one is not. It's a fake. Looking at the photograph, I think it's quite difficult. At least I could not make out which one was the real one. So there can be a chance or coincidence, and that's also a barrier to reliable evidence. So the one on the left is actually the true Donald Trump. The one on the right is a fake. Now, what are the essentials of evidence-based medicine? So you generate a clinical question based on the needs, could be diagnostic, prognostic, therapeutic, track down efficiently the best available evidence. You critically evaluate the evidence for its validity and clinical usefulness. You apply those results to practice, and then you evaluate the performance. Traditionally, narrative reviews were used to synthesize evidence, and this was not too long ago, maybe just about 15-20 years ago. They would provide an overview on a particular topic, generally written by an expert or an authority in the field, who would do some Medline search for trials and information, also by personal contacts and communication with other opinion leaders in the field. There would be a brief discussion of trials for and against, and that would lead to some inference and conclusion, which may or may not have potential to influence practice. Now, what were some of the problems with narrative reviews? They were generally not evidence-based, more of eminence-based, and jokingly I say more of senescence-based, because it was generally done by the older people. Prone to several biases and errors. Mostly they lacked description of search methodology. They would also lack objective assessment of the quality of primary studies. The quality assessment of primary studies was not so much in vogue 20 years ago. The literature search would be haphazard or selective. Those narrative reviews were generally not very reproducible. Neither the readers nor others could actually judge them or replicate them. Most of the time, they were qualitative reviews with data synthesis not happening. And sometimes there would be multiple reviews, and there would be a lack of agreement between two reviews. They were hardly updated, and hence they mostly lagged behind time. And that is the reason systematic reviews came into the picture. A formal definition, again, for the benefit of trainees and students, a systematic review is defined as a summary of the medical literature that uses explicit methods to perform a thorough literature search and critical appraisal of individual studies, and that uses appropriate statistical techniques to combine these valid studies. Most systematic reviews evaluate the effectiveness of therapy, but you could have systematic reviews of all kinds of healthcare interventions, including diagnostic test accuracy, including observational studies, including prognostic studies and biomarker studies. Why are they systematic? They are systematic in identification of the literature. They are very explicit in statement of their objectives, materials, and methods, and largely reproducible in methodology and conclusions. And by far, the best individual source of systematic reviews is the Cochrane Library. The Cochrane Library was actually available to the entire country free of cost, provided by an agreement between Wiley, the publishers, and the Indian Council of Medical Research till few years ago. However, that contract was not renewed, and now the Cochrane Library is available only for a subscription. However, the recent draft policy of the Government of India suggests that not only the Cochrane Library, but all major scientific journals should be accessible to all researchers throughout the country. So possibly in 2021 or 2022, everybody would have access to most biomedical journals that are published in the world in India. So how are systematic reviews better? They are better because they have a focused, well-defined research question, clearly stated aims, objectives, materials, and methods. The literature search is comprehensive, exhaustive, and repeatable. They use explicitly predefined inclusion-exclusion criteria. There is a critical appraisal of quality assessment of primary studies. There is a clear analysis of the results, could be qualitative, but more often quantitative. Small effects can be picked up by pooling data in the meta-analysis, and they have a clear structured reporting pattern, and hence the interpretation of results is easy. Systematic reviews are generally updated periodically to keep abreast with time, and because they are more objective, they are much less prone to bias and error. Now, when should one do a systematic review? So systematic reviews are indicated when several trials answering the same question are present, but many of them show non-significant results, or when different trials on the same question provide conflicting and contradictory results. You could also do a systematic review when you want to have the information on the magnitude of treatment effect, and when objective answers are required that call for or refute the need for further clinical trials on a particular question. Now, what is a meta-analysis? Meta-analysis is generally done as a part of a systematic review. The formal definition as given by Egger was it's a statistical analysis of the results from independent studies, which generally aims to produce a single quantitative estimate of the treatment effect. The term was first coined by Glass in 1976, and as I said, it's generally done as part of a systematic review. Now, this is in brief a abridged history of systematic reviews systematic reviews and meta-analysis. So literature reviews, the narrative reviews first started in early 1900. The first modern meta-analysis was actually published by Smith and Glass in 1977. And since 1990s and 2000, there has been an explosion in popularity of systematic reviews and meta-analysis in biomedical research. So what happens in a meta-analysis? The main outcome is the overall magnitude of the effect and how it differs between subjects, protocols, and researchers. It's just not a simple average of the magnitude in all the studies. Meta-analysis typically gives more weight to studies with more precise estimates. And the weighting factor is almost always 1 divided by square of the standard error. The standard error here is the expected variation in the effect if the study was repeated again and again. So if all other things equal, this weighting factor is generally related to the study's sample size. But it's not only the sample size, it also takes into account differences in error of measurement between the studies. So what are the questions that a meta-analysis addresses? One is, what is the direction of the effect? What is the magnitude or size of that effect? Is the effect consistent across different studies? And what is the strength of evidence for this effect? So as I said, meta-analysis is generally done as a part of the systematic review process, but sometimes it is also done outside of a systematic review. What are the steps in conducting the systematic review? So this is from the Cochrane collaboration. They suggest a 10-step process. So you formulate the research question, put together a team, register the title. This is required compulsorily for Cochrane reviews, not necessarily for all other reviews. You write a protocol, locate and select studies, assess the studies for the risk of bias, extract relevant data, analyze and present the results, interpret the results, and write the formal review, and subsequently improve and update the review over time. So this, in a sense, is what the steps for conducting a systematic review are all about. Now, most systematic reviews and meta-analysis use something known as the PICO approach, wherein PICO stands for population or participants, I for intervention, C for comparator, and O for outcome. And in recent times, this has been slightly modified, and it's called the PICO-TS approach, where T is the time or duration of the study, and S is the study design, whether it was an experimental or an observational or a randomized controlled trial. So this is the framework on which a systematic review and meta-analysis is generally conducted. So what are the issues that one faces while formulating a question for a systematic review? You could ask narrow versus broad questions. Some questions may be clinically meaningful and useful. Others may not be so clinically meaningful and useful. Very broadly defined questions can certainly be criticized for mixing apples and oranges, but very narrowly focused questions can have very limited generalizability and sometimes can lead to biased interpretations and conclusions. So you have to be careful while formulating the question for your systematic review and meta-analysis. There are certain elements of a good research question, and this simple acronym of sample is actually useful to remember. So is your question specific? Is it answerable? Are there measurable constructs? Is it practical? Is it logical? And is it empirical? So if your research question has all these elements, then it probably would qualify as a good research question. Now, this is an example of a well-formulated research question, and here you can see the PICO depicted here. So if one asks the question, does altered fractionation radiotherapy improve survival outcomes in patients with loco-regionally advanced head and neck squamous cell carcinoma compared to conventional fractionation? And you could break it down into the PICO. So the participants here are patients with loco-regionally advanced head and neck squamous cell carcinoma. The intervention is altered fractionation radiotherapy. The comparator is conventionally fractionated radiotherapy, and the outcome is survival. So a well-formulated research question should actually reflect the PICO framework. You need to define your inclusion and exclusion criteria quite clearly for your systematic reviews. So they have to be based on predefined criteria. Are the right type of studies included to answer the question? The general dictum is to restrict to one study design for one particular question. So you should not try to pool data from observational studies with data from randomized controlled trials. Studies should be defined according to their design, participant characteristics, interventions, and outcomes, and 2 reviewers should independently assess each study. Having a scoring sheet or a checklist generally helps in this case. So how do you locate and select studies? One thing that I always emphasize is please take help from the information specialist, the librarian. We generally tend to forget the librarian, but they are very useful when it comes to a comprehensive and systematic search of the medical literature. So you could look through databases, conference proceedings, the gray literature, cross references, contact experts and authors. In the COVID era, something that has become very popular is the preprint servers. Not that they did not exist prior to COVID-19, but I think their popularity has has skyrocketed in the last 9-10 months. So you have the Med Archive, the Bio Archive, the Research Square, SSRN, a lot of preprint servers where many of the manuscripts are immediately posted once the manuscript is drafted. You also have to look at publication bias, and there are several unpublished studies. So negative studies generally don't get published, so you have to try and find the unpublished studies as well. The bottom line is that you have to have an explicit search strategy with a defined cutoff date. What about data extraction and abstraction? So the list of data to be extracted has to be agreed upon a priori during the design stage of your systematic review. You cannot start to extract data and then later on say, no, we needed to extract this also, we needed to extract that also. So you have to agree upon what all data will be extracted from the primary studies. So review specific data extraction form is typically needed so that the same data is extracted from each individual study and missing data are clearly apparent. It is recommended that data extraction be performed by at least 2 independent reviewers, and any discrepancy should be resolved by consensus by the 3rd reviewer. The collected data would typically include the study characteristics, the sample demographics, and the outcome data. So you could do a qualitative synthesis, which is descriptive summary of the results, but more important and more often you are interested in doing a quantitative data synthesis, which is the meta-analysis. So you pool data where there are little differences between studies, the outcomes have been measured in the same way, and the data, most of the data is available from the reported analysis. The statistical considerations that are present for data synthesis include the study weightage for statistical pooling, the different statistical methods available for pooling, and the subgroup analysis and the sensitivity analysis. Now, what are the measures of effect in a systematic review and meta-analysis? The strength of a relationship between 2 variables is the unit of analysis in a meta-analysis. And the effect measures from different studies should be comparable to one another. That is, they should be measuring the same thing. One study, if it measures something else and the other study measures something else, you cannot pool that data for that from those 2 studies. Estimates of the effect measure should be computable from the information that is likely to be reported in published reports. One should not be needing to require a reanalysis of the raw data. Reanalysis of the raw data is typically required when you do an individual patient data meta-analysis. Your effect measure should have good technical properties, that is, its sampling distribution should be known so that the variance and the confidence intervals can be computed robustly. Now, you can combine effects from different studies only when they are expressed in the same units. In most meta-analysis, the effects are converted to a generic dimensionless measure. So for continuous outcomes, it could be the standardized mean difference or the change in the mean. And for binary outcomes, it is typically the risk ratio, the odds ratio, hazards ratio, and the risk difference. Now, what are the measures of relative frequency? As I said, you could measure the relative risk or the risk ratio. So when the dependent variable is a frequency of something, effects are expressed as ratios. So simple example here, relative risk or risk ratio. So if 10% of active people and 25% of inactive people get cancer, the relative risk of cancer for inactive versus active is simple here. It's 25 divided by 10 or 2.5. Hazard ratio is quite similar to the risk ratio, but it is defined as the instantaneous risk ratio. The odds ratio is slightly different. So the odds ratio for the same data would be 3 instead of 2.5. And odds ratio is mostly used for case control studies. It's generally hard to interpret, but if the frequencies are less than 10%, then generally you would have very little difference between the risk ratio and the hazard ratio. For the most part, for survival outcomes and time to event outcomes, most people use the hazard ratios, which are much more intuitive and meaningful. So so this is a similar example. So the risk ratio here is A by N1 divided by C by N2, where A and C are the events in the treated and control, and B and D are the non-events, and N1 and N2 represent the number of patients in the treated and control. The odds ratio, as I said, becomes A into D by divided by B into C. And the risk difference would be defined as A divided by N1 minus C divided by N2. It's also important to define whether it's an adverse outcome like death or a beneficial outcome like locoregional control. Because for an adverse outcome like death or failure, the OR, HR, or RR less than 1 will mean that the new intervention is better. Whereas for a beneficial outcome, say clinical improvement, locoregional control, and OR or RR of less than 1 would actually mean that the new intervention is worse. So you need to be very clear whether you're reporting an adverse outcome or a beneficial outcome. What are some of the statistical models that are available for pooling data? So the first and the commonly used model is the fixed effects model, which assumes that there is a single true value underlying all the study results. If all the studies are extremely large, they would have identical estimates of the treatment effect. This fixed effect model actually ignores the between study variation or heterogeneity. The second model is the random effects model, and that's a more appropriate model to use because it assumes that studies are a random sample of studies addressing related questions, and the results differ by chance and by differences in the questions. And each study will estimate a different underlying true effect. It assumes that there is no single underlying value of the effect, but that there is a distribution of effects around a mean value. The random effects model generally tend to produce wider confidence intervals as it is a more conservative estimate. In the recent times, beyond the random effects model, the meta regression approaches are being used, wherein they are supposed to be used when there is significant methodologic heterogeneity, and you could use advanced Bayesian analysis to get more robust estimates. Significance testing and p-values. So p-value is a measure of statistical significance which tells us the probability of an event occurring due to chance alone. Like in all other branches in statistics, the p-value ranges from 0 to 1. The closer the p-value is to 0, the less chance there is that the effects of the two interventions are the same. And again, by general principles, a p-value of less than 0.05 are used as a statistically significant result, although this is quite arbitrary. So as I said, a p-value of less than 0.05 would indicate that the result is unlikely to be due to chance. A p-value of more than 0.05 indicates that the result might have occurred due to chance. P-values do not indicate the magnitude of the observed difference between treatments that is needed to determine the clinical significance. And ideally, one needs to report confidence intervals also. What is a confidence interval? Confidence interval is the range within which we have a measure of certainty that the true population value lies. The CI around a result obtained from a study sample indicates the range of values within which there is a specific certainty that the true population value for that result lies. In general, the 95% confidence level is used. Therefore, the 95% CI is the range within which we are 95% certain that the true population value lies. So these 95% CIs, they state whether the result is significant or not. The width of the interval indicates precision. Wider intervals suggest lesser precision. They show the strength of the evidence, strong or weak. The line of no effect centers around unity or 1, and if the CI straddles unity, it indicates no statistically significant differences between the two groups. Coming to the second part, which is looking at or interpreting the output from a meta-analysis, which is the forest plot, and we chose the research question as does altered fractionation radiotherapy improve survival in patients with locoregionally advanced head neck squamous cell carcinoma compared to conventional fractionation. So this meta-analysis tried to answer that question. This is the forest plot, and we will delve slightly deeper into the forest plot to understand. So the names or labels on the left are the studies or authors of the primary studies. So if you look on the left are the names CORTC, RIO, RTOG. So these are the studies or authors of the primary studies. The small squares represents the results of the individual trial results. So these small squares, they represent individual trial results. The size of each square represents the weight given to the study in the meta-analysis. So you can see that some are larger squares, some are smaller squares. So the size of the square is proportional to the weightage given to that study. The horizontal lines associated with each square represent the confidence interval associated with each result. So you can see there is a horizontal line with each square, and that represents the confidence interval around the point estimate for that particular study. The solid vertical line represents the line of no effect. So you can see there is a solid vertical line, and there you can see that the hazard ratio there is 1. So that's the line of unity or line of no effect. The weighted pool analysis is given a diamond shape, and the center of the diamond is the overall point estimate through which the dotted line runs, while the horizontal width of the diamond is the confidence interval around it. So you can see that this is the overall diamond for this analysis, but it is subgrouped by hyperfractionation, accelerated fractionation without total dose reduction, and accelerated fractionation with total dose reduction. So each of these subgroups have a diamond associated, and this is the overall effect size. And as you can see, the dotted line runs through the center of this diamond. So the point estimate here is 0.92. So the risk of the hazards of dying are reduced by 8%. The relative risk is reduced by 8% with altered fractionation radiotherapy compared to conventionally fractionated radiotherapy, and that is statistically significant. The p value, the test chi-square test for interaction is 0.02, and as you can see, this does not straddle the line of unity. So this is just again in some more detail, slightly enlarged view. So labels or names of the studies or authors of primary studies, the size of the square and the line across them indicating the weightage given and the confidence interval around that study. The diamond is the pooled estimate. The vertical solid line is the line of unity, and the dotted line is the line that passes through the center of the diamond. So as I said, once again, size of the square is proportional to the weight of the study. The horizontal lines are confidence intervals of individual studies. The diamond shape is the weighted pool effect of all studies, and the horizontal width of the diamond is the overall confidence interval. Now, we do come across heterogeneity in systematic reviews and meta-analysis, and heterogeneity is observed differences in results of different trials. If too much heterogeneity, then it may be inappropriate to pool data. So you could have clinical heterogeneity, you could have methodological heterogeneity, and you could have statistical heterogeneity. There are certain tests that assess heterogeneity, and the two common ones that meta-analysis uses is the Cochrane's Q test of heterogeneity and the I-squared statistic of heterogeneity. And the null hypothesis for the test of heterogeneity is that the treatment effect is the same for all studies being analyzed. So if you see in the Cochrane Q test for heterogeneity here is showing a p-value 0.001, which means there is significant heterogeneity amongst the studies that have been included in that particular meta-analysis. The I-square statistic, more commonly in use in the last few years. So an I-square of more than 0.5 indicates that heterogeneity is high. If it is less than 0.5, it means that it is not very heterogeneous. So when can meta-analysis be misleading? When it is done outside of a systematic review, when poor quality studies are included, or when you don't do a proper quality assessment, when inadequate attention is given to heterogeneity, indiscriminate data aggregation can lead to inaccurate conclusions, and when reporting biases are a problem. And you could have all sorts of biases, and we'll come to that section of what are the biases and how to deal with biases. So the Cochrane collaboration developed a risk of bias tool. There are problems with the design and execution of individual studies, and in clinical trials, they have broadly categorized as selection bias, performance bias, detection bias, attrition bias, reporting bias, and other biases that do not fit into these categories. And the risk of bias tool from the Cochrane collaboration uses 7 specific domains: sequence generation, allocation concealment, blinding of participants, blinding of outcome assessors, incomplete outcome data, selective outcome reporting, and other potential sources of bias. So this is the 7 criteria that need to be considered. So it's very well known that non-randomized trials overestimate treatment effect compared to randomized trials, or poorly randomized trials also tend to overestimate treatment effect. So randomization is the basis. One of the things that you look in a randomized controlled trial is whether there has been an adequate sequence generation. So there are several methods of generating a random sequence, and the ones in the black there are all valid methods: tossing a coin, using a computer program, throwing dice, random number table. However, the ones in red are not valid ways to generate a random sequence. So by day of the week, or by date of birth, or by odd or even number, or by patient reclination preference. The second important aspect of randomization is allocation concealment, which is protection of the random sequence. And this is supposed to be the single largest source of bias in randomized controlled trials. Inadequately concealed or trials with unclear allocation concealment tend to overestimate effects by more than 30%. So how does one assess whether the random sequence has been protected? So again, the ones in black are valid methods: sequentially numbered identical drug containers, allocation in a sealed opaque sequentially numbered envelope, central allocation by telephone or IVRS or email. However, the ones in red, an open randomization schedule by alternation, envelopes without appropriate safeguards, and by date of birth or hospital number, do not lead to sufficient protection of the random sequence. So they do not conceal the allocation. Performance bias, that is taken care by blinding of patients, caregivers, and outcome assessors, and inadequately blinded or open trials tend to overestimate results compared to adequately blinded trials. Attrition bias refers to incomplete outcome data lost to follow-up, dropout, exclusion, and they can bias the results if those who drop out are different from those who remain in the trial. And the possible effects of dropouts can be evaluated by conducting a sensitivity analysis. Another important source of bias is the publication bias. We all know that positive results tend to get published, whereas negative results are not published. So published effects tend to be larger than true effects. And a plot of the standard error versus effect magnitude should have a triangular or funnel shape. Any asymmetry in the plot can indicate that non-significant studies weren't published. So if you get a asymmetry in the funnel plot, it just means that there is some publication bias. It's still not very clear how to best deal with it. You can just report the presence of a publication bias. You cannot correct for the publication bias. Now, what is a sensitivity analysis? It's an analysis that provides information about whether assumptions and decisions made during the meta-analysis have a major effect on the results. It It's the repetition of the analysis using different assumptions, generally done by dropping one study at a time. So if studies were excluded because they were judged to be of poor quality, what is the effect on the results if they are included? If one study is an outlier, what is the effect of excluding it? And both fixed and random effects analysis can be done to see if results are significantly different. We talked about risk of bias. Cochrane collaboration has also developed something known as the grade recommendation, which is grading of recommendations, assessment, development, and evaluation. So this is categorized into four categories. One is very low, which is we are very uncertain about the estimate. Two is low, that further research is very likely to have an important impact on our confidence in the estimate of effect and likely to change the estimate. Three is moderate. Further research is likely to have an important impact on our confidence in the estimate of the effect and may change the estimate. And four is high grade of evidence, which is further research is very unlikely to change our confidence in the estimate of effect. So what does the grade criteria use? Five criteria the grade uses, which is limitations, inconsistency, indirectness, imprecision, and other biases. If all of these criteria, if all of these are low, then the quality of evidence is high, or vice versa. If any of this is present, then it downgrades the quality of evidence. Now, there are several criticisms of meta-analysis, but I always believe that a meta-analysis is only as good as the studies that are included and the methods that are applied. So if you put garbage in, you will get garbage out. In recent times, it has become important to register your systematic review and meta-analysis, and there are two large such registries. The first one was by the NHS, the Prospero registry, which is an international registry of systematic reviews. And more recently, there is another registry, which is the International Platform of Registered Systematic Reviews and Meta-Analysis Protocols, the INPLASI. So you could register your systematic review protocol at either of these two registries. Systematic reviews now also have something known as a preferred reporting in systematic reviews and meta-analysis, or the PRISMA statement. This is a diagrammatic representation. It's now mandatory for reporting all systematic reviews and meta-analysis. So it sort of is looks at how you identified the primary studies, how many were screened, how many were excluded, what was the eligibility, how many were assessed with for full text eligibility, and finally how many were included in the synthesis of results. So Prisma flowchart is now the figure 1, just like the consort diagram is the figure 1 for all randomized controlled trials. The Prisma flowchart is the figure 1 for all systematic reviews and meta-analysis. This is the Prisma checklist. This is also an integral part of reporting now. So it has 27 domains, and you have to identify on which page of the manuscript this particular domain is present. So how do we sort of classify or divide meta-analysis? So you could do a meta-analysis, define them by data type. So literature or published data-based. Second could be individual patient data-based. You could also define them by study type. Meta-analysis of observational studies in epidemiology, meta-analysis of diagnostic test accuracy, meta-analysis of intervention studies. Also by the model type, whether you use a fixed effect model, a random effect model, or a meta-regression approach. And finally, by the methodology that you use, which is the indirect comparison meta-analysis, the direct comparison meta-analysis, or the mixed treatment comparison or network meta-analysis, which has become increasingly popular in the last 5-10 years. So we'll briefly discuss about indirect comparison and direct comparison and some of the work that we have done in this field. So indirect comparison meta-analysis. So by if you look at this cartoon, it looks very simple. If we know how much taller is B to A and how much taller is C to A, we can find out how much taller is B compared to C. And this is for any pair B and C, this is the mean advantage of C over B, which is the advantage of C over A minus the advantage of B over A. So this is a complex calculation. I don't think you need to get into the complexity of it, but this was described by several people in early 2000. So we tried to answer a question using the indirect comparison methodology. So the condition of interest is locoregionally advanced head and neck squamous cell carcinoma. Many trials compare concurrent CTRT with RT alone. So concurrent CTRT is the investigational treatment there, and standard fractionated RT is the control arm. Some others compared altered fractionation RT with standard fractionated RT. So investigational treatment B compared to standard treatment C. Our interest was the comparison of treatment A with treatment B. So concurrent chemoradiotherapy versus altered fractionation radiotherapy in locoregionally advanced head and neck squamous cell carcinoma. Now, some of the core assumptions of indirect comparison are similarity, homogeneity, consistency, and independence. And effect A versus B is measured against a common comparator C, which is the conventionally fractionated RT, by contrasting the estimated effects of A versus C and B versus C. So this was published a few years ago, and what we demonstrated was that we use actually two methods: the inverse variance fixed effect methods and the Simonian layered random effects method. And as you can see, the HR for hyperfractionated radiotherapy was not very different compared to conventionally fractionated radiotherapy. But accelerated radiotherapy without total dose reduction and accelerated radiotherapy with total dose reduction were actually worse than concurrent chemoradiotherapy. So this was the typical indirect comparison flow chart. This is the forest plots of CTRT versus all forms of altered fractionation radiotherapy. Again, as you see, hyperfractionated radiotherapy, there was no difference in HFRT versus concurrent chemoradiotherapy. Sensitivity analysis did not show any single study driving the results of the meta-analysis. However, there are several limitations of indirect comparison meta-analysis, and it is generally not used to change practice. The thumb rule is that direct comparison from one RCT is as precise as an indirect comparison from 4 RCTs, assuming equal variance of all paired comparisons. So one RCT, direct comparison RCT, would be equal to 4 indirect comparisons that we use in an indirect comparison meta-analysis. So we went ahead and did a direct comparison meta-analysis. This was published again a few years ago in Clinical Oncology. So this was looking at a direct comparison of concurrent chemoradiotherapy versus altered fractionation radiotherapy in definitive management of locoregionally advanced squamous cell carcinoma. Again, the Prisma flow diagram. The primary outcome of interest was overall survival. And as you can see, the overall survival was significantly better with CTRT compared to altered fractionation radiotherapy alone. Even secondary outcomes of interest such as disease-free survival and locoregional control were better with CTRT. Grade 3/4 mucositis was marginally higher, and grade 3 or worse late xerostomia was significantly lesser with altered fractionation radiotherapy. The funnel plot showing no significant publication bias. There was a low risk of bias for efficacy outcomes, but there was a high risk of bias for the toxicity outcomes. And this is the summary of findings table from the grade recommendation. So there was moderate quality evidence that CTRT was better than altered fractionation RT for efficacy outcomes in definitive management of head and neck squamous cell carcinoma. The third comparison is the mixed treatment comparison, which combines the indirect and the direct comparisons. And this is mixed treatment comparison or network meta-analysis of altered fractionation radiotherapy and chemotherapy in head and neck cancer. And this was published in the JCE around 7-8 years ago. So as I said, the network meta-analysis integrates results of all available direct and indirect comparison. And what the network meta-analysis or the mixed treatment comparison meta-analysis showed was that if you combine concurrent chemotherapy with altered fractionation radiotherapy, that has the potential to be the best treatment in terms of overall survival. Now, we all know that there is a significant time lag between publication of a primary study and inclusion in a systematic review. And this figure here, this is the time in years, and these are the different research studies. So as you can see, the most of these studies, they take at least 3 to 5 years before they are included in a systematic review. And hence, most systematic reviews and practice guidelines become outdated by the time they are published. And that brings in the concept of living systematic reviews and living practice guidelines, which are the new kids on the block. This concept was initially proposed in 2014. Living systematic review is defined as a systematic review that is continuously updated. There is an explicit and a priori commitment to frequency of search and updates. It incorporates relevant new evidence as and when it becomes available, which helps to narrow the evidence practice gap. The living guidelines are an optimization of the guideline development process, which allows updating the guidelines as the newer evidence becomes available. This has gained a lot of traction and popularity in the ongoing COVID-19 pandemic and is being used and refined by Cochrane as well as non-Cochrane networks. So when are living systematic reviews and guidelines appropriate? When the question is of sufficient importance and high priority for decision making, the certainty in the existing evidence is low or very low, new research evidence is emerging rapidly and continually, and new research evidence is likely to change results or inferences. So this is the emerging health knowledge ecosystem. And as I said, initially the living systematic review was proposed in 2014, but it has come a long way and has become quite popular during the COVID-19 pandemic. This is just an example of living systematic review and network meta-analysis. This is the last update as of 17th December 2020. And this was initially published in July 2017, and every month is being updated by the BMJ. So the COVID-19 has actually brought living systematic reviews and network meta-analysis right to the forefront of medical research. So before I end, I would just like to invite all of you to the 19th Annual Conference of Evidence-Based Management of Cancers in India at Tata Memorial Center. It's a virtual meeting, so each one of you can register and participate. The topic is Technology and Cancer Care, Promise and Reality of the Brave New World. Thanks for a patient listening, and I'm happy to take questions.
Thank you, sir, for that excellent discussion, as well as letting us know about the newer changes about this living systematic reviews and living about the treatment decisions. So, anyone has a burning question can, unmute themselves and ask the question to sir directly. So if anyone doesn't, I have a question myself. Sir, while doing a meta-analysis of a number of non-inferiority trials, now these trials use different margins for non-inferiority. Now, does that have a bearing on the result, or is that a potential source of bias?
So I don't think, I don't know the right answer, but I don't think whether it is a superiority design or an equivalence design or a non-inferiority design. When you are pooling data from the meta-analysis, you are looking at the comparison between the two arms. So it really doesn't, the interpretation of the primary study will be completely dependent on whether it used a non-inferiority design or a superiority design or an equivalence design. So is the sample size calculation and other things. But as far as the meta-analysis is concerned, I think it really does not matter what design you have, what design the primary study has used, because you are actually using the hazard ratios, or you're using the number of events that have happened in the test arm versus the control arm. So technically speaking, it really does not matter what phase. So there are several randomized phase 2 studies, and there are several studies which use in non-inferiority design. It really doesn't matter as far as the meta-analysis is concerned.
Okay, sir. Okay, so question would be, yeah, so would you please throw some light on network meta-analysis? Is a question from Dr. Riddhi Jyoti Talukdar.
We just the last couple of slides were on the mixed treatment comparison or network meta-analysis. So essentially, COVID is a great example actually of you have hundreds of interventions being tried out for COVID. Now, how do you rate the comparative effectiveness of remdesivir versus convalescent plasma versus favipiravir versus XYZ? That is where the concept of network meta-analysis comes. So you actually, the comparative effectiveness of different interventions is best assessed by using a network meta-analysis. You would not have a randomized trial. I mean, although the recovery and solidarity used multiple sort of interventions compared to the standard of care or control arm, but even those interventions were limited to 3 or 4. So when you have a large number of interventions being tested, and if you need to compare the effectiveness of different interventions, the network meta-analysis becomes important, because it compares. So outside, so you don't have a primary comparison of say favipiravir with remdesivir. You don't have a randomized trial that has compared favipiravir with remdesivir, but you have a randomized trial that has compared favipiravir with the standard of care and remdesivir with the standard of care, and then you can actually use the network methodology to compare favipiravir versus remdesivir. So I think the COVID has really made this the mixed treatment comparison and network meta-analysis was not very commonly done. Certainly not. It's not very common in oncology. We did one last year actually in elderly glioblastoma. It's not a common thing to be done in oncology, but it's quite common in cardiology, psychiatry, and now in infectious disease.
Thank you, sir. The next question is that many meta-analyses are skewed by an outlier bunched up into a list of low-powered studies. To how to judge the strength of a meta-analysis, and can there be a meta-analysis of meta-analysis?
So the first question first. So I did show that by using a sensitivity analysis, you can actually so you drop. There are two ways in which you can handle this. One is to do a subgroup analysis of say conducted studies versus high quality studies versus low quality studies. That's one way to do it. Another way to do it is to drop the poor quality studies and see whether that influences the conclusion, the results, the inferences, and the conclusions. So they are very well, both these methods are very well defined and described to assess to handle this situation of poor quality studies skewing the results of meta-analysis. You generally don't have a meta-analysis of meta-analysis, but you do have an overview of systematic reviews. And for meta-analysis, you have to include the primary studies. So you cannot do a meta-analysis of the meta-analysis. You will have to, your input will have to be from a primary individual study for a meta-analysis.
Very well said, sir. So any other questions? Again, you can unmute yourself and ask the question directly. So if there aren't any, so then
sir,
Achha, yeah.
sorry.
Go ahead.
Sir, could you highlight just for the completion's sake, could you highlight some of the pitfalls or the caveats in network meta-analysis? Because I think people are taking this a bit too far nowadays, especially in a few cases in oncology. They have started comparing things like radiation and chemotherapy. And I am a bit skeptical about including those kind of studies in a network meta-analysis, especially for gallbladder cancer. I think they've done one, or maybe for pancreas, I forget.
So there's no question that the direct comparison meta-analysis remains the most sort of robust way to grade the evidence. I mean, on the you would do a network meta-analysis only if you don't have a direct comparison between two treatments. So if you don't have a direct comparison between radiotherapy and chemotherapy, I'll give you the example of, say, glioblastoma, where there is a comparison of in the elderly glioblastoma of radiotherapy versus temozolomide chemotherapy. So if you
Not a
didn't
trial.
have that
Yes,
kind
yes.
of a direct comparison, you could try to infer that through a network meta-analysis. But again, the network meta-analysis and the indirect comparison meta-analysis, there are certain assumptions that need to be met for those kinds of meta-analysis, and they generally should not. So the network meta-analysis actually just ranks the treatments, that this treatment is likely to be superior to the other treatment. It doesn't give you a point estimate. It doesn't give you a confidence interval around that point estimate. You cannot
Yes.
really use those to change practice. So from the network meta-analysis, if you get something, so suppose you get that temozolomide is superior to radiotherapy in elderly glioblastoma, then that is food for thought that maybe a well-powered, adequately powered randomized control trial could compare these two and provide you the definitive answer.
So again, it should be used more as hypothesis
Yes,
and
yes,
research
yes,
generating than
yes,
clinical practice changing.
absolutely. It should not
Yes,
just
sir.
change
Thank you.
practice.
Thank you, sir. That's what I wanted to highlight, sort of. Thank you.
Thank you, sir, for that excellent presentation and the discussion which we had at the end. So, thanks a lot for participating. I think that's it for today. So, we meet again next week for the last day of this course on critical appraisal of medical literature. So, till then, goodbye and good night. Thank you.
Thanks,
Thank
Sayan.
you all.
Thanks.
Thank you, sir.